Last time we discussed what happens to the maximum value when the iterative elimination of dominated strategies is applied. So in this module we are going to discuss what happens to the equilibrium, the pure strategy Nash equilibrium after such elimination. Now, so the first thing that you can notice, even without any kind of domination, is that if there are two games in one of which you have removed one strategy, and if in the reduced game the PSNE of the original game survives in that reduced game, then that should be a PSNE even in that reduced game. So here is the formal statement. It says that suppose you have G and G hat. These are the games before and after elimination of a strategy. And then A star is a PSNE in G, the original game, and it continues, so it survives in the reduced game G hat, then it is going to be a PSNE in that reduced game as well. And I'm not going to prove it formally, it is very straightforward. So the intuition is essentially that PSNE is essentially giving you the maxima. So for every player at that point, in that equilibrium point, if you move from that equilibrium to any other strategy, you are not going to increase your payoff. So therefore, if you remove something else, it does not really matter. It still keeps the maxima to be the maxima. So therefore, it is always going to be the Nash equilibrium for that reduced game. So write that formally to prove this theorem. The question, the more important question is, can you generate new equilibrium? So that is not quite obvious. So maybe you have removed some strategies, and because of which now you have not only one maxima but multiple maxima. So you can possibly have multiple PSNE. So the next theorem actually demystifies that fact. It says that no, you cannot have a new equilibrium generated. It says that suppose you have a normal form game G, and suppose SJ hat is a weakly dominated strategy. So here you need the idea of domination. So if you just arbitrarily delete some strategies, it may be possible. But if you are removing only weakly dominated strategies, then you won't be creating new equilibrium. Now it is saying that if G hat is the reduced game, after eliminating SJ hat for player J, then every PSNE of that reduced game is a PSNE of G. But in the process of elimination, you might have lost some PSNE. That is entirely possible. So you have removed some PSNEs, but you cannot create new PSNEs. So you can actually look at the previous example where we did iterated elimination of dominated strategies. Look for PSNEs in that game. Very likely that game must have more than one PSNE, and you will see that after the elimination is done, some of the PSNEs have disappeared. The final thing that you got is definitely a PSNE, but you have actually lost someone. But the PSNE in that reduced game is definitely going to be a PSNE in the original game. That is the conclusion of this. And the proof is fairly simple and straightforward. So all that we need to see, so let us first define what the reduced game is. In the reduced game, let us denote the strategy sets with that hat, SI hat. So for all the agents except agent J, the strategy set remains the same. So that is the case here. Only for player J, the strategy set gets reduced by 1. The size of the strategy set gets reduced by 1. Now what we will have to show is that this A star, which is a PSNE in the reduced game, it should also be a PSNE in the original game. So let's go over it. So because it is a pure strategy Nash equilibrium in the reduced game, this inequality must hold. So here I am just writing this is J star, comma S minus J star in shorthand notation. Now for all the players, for all the agents I except agent J, this must be true, and here all these SIs will come from the SI hat, which is actually equal to the original game's strategy. So their strategy has not been removed, so therefore their strategy set remains the same as the original game. But for player J, if you write this is coming from the reduced set, so SJ hat, which has one less strategy than the original game. Now we'll have to show that there is no profitable deviation for any player in G. So this is very obvious for the players except agent J, because for them this inequality is the same inequality as in the original game. So there is nothing to show there. The interesting part is for player J, we'll have to show that this is true. So this inequality is true for all the strategies except strategy SJ hat. But we'll also have to show that this inequality holds even when you consider SJ to be in SJ, that is, you also include SJ hat. So, and that is the place where we will be using the fact that SJ hat is a dominated strategy, right? So since SJ hat is dominated, then there must exist some TJ, and now this TJ must exist in the reduced set, so the set that we are considering. Because it has to be different from SJ hat. So you have this inequality satisfied for all the S minus J in capital S minus J. So here for all the agents except agent J, this set is same as S minus J hat. So I have just used the same S minus J. Whether it is the original game, it's the reduced game, does not matter, it's the same. In particular, if you want to focus on S minus J star, that is the Nash equilibrium strategy in the reduced game for all the players except agent I, except player J, this should also hold for that inequality as well. Now it is very clear. So S star is a PSNE in the reduced game, and TJ was also a strategy in that reduced game. So therefore, this must hold. This is by the definition of the PSNE in the reduced game, and this inequality is something that we have just shown. This is going to be greater than or equal to UG of SJ hat. So all that we wanted to show is that this inequality of SJ star, so this inequality of UJ S star should be greater than or equal to, for all SJ, it was always satisfied for all the strategies in the reduced set. Now it is also getting satisfied for the SJ hat, and therefore we can actually complete the conclusion that it is a Nash equilibrium even in the original game. So let me summarize all the things that we have just seen here. So we have seen that elimination of strictly dominated strategies have no effect on PSNE. And we have seen that the elimination of weakly dominated strategies may reduce the set of PSNEs but never adds new. This is something that we just saw. And the max mean value in the previous module, you saw that it is going to be unaffected by the elimination of the strictly or weakly dominated strategies.